First, I will introduce my group members. First, Mukri Shazani bin Mustaqim, Alexander Koi Kaisheng, me, Sofia Haini binti Mak Razali, and last, Mohammad Zulkarnain bin Junaidi. First, introduction. This presentation applies numerical method to analyze renewable energy data for the year 2018. Two interpolation techniques are used, namely Lagrange interpolation and Newton divided difference to estimate and analyze energy generation values. This method helps demonstrate how numerical techniques can be used to model real engineering data and support database decision making.
Assalamualaikum and good day. My name is Mukri. I'm going to continue methodology. This section explains the systematic procedure used to analyze renewable energy generation data for the year 2018 using numerical interpolation technique. The methodology involved data selection, formulation of interpolation models, application of Lagrange interpolation, and Newton divided methods, implementations using coding, and comparison of the result obtained. For the interpolation model formulation, interpolation is used to estimate unknown values within the range of the known data points. In this study, interpolation polynomials were formulated using two numerical methods, Lagrange interpolation and Newton divided difference. Both methods aims to construct a polynomial function that passes through all given data points. Once a polynomial is obtained, it is estimate renewable energy value at a selected point within the database range, dataset range. For the Lagrange interpolation method, the steps involved in this method are identify unknown data points from the dataset, construct the Lagrange basis polynomial for each data point, combine all basic polynomial to form the final interpolation polynomial, and the last one is substitute the required value into the polynomial to estimate the unknown energy generation value. For the Newton divided difference method, the procedure includes arrange the data points in tabular form, compute the divided difference for each order, construct the Newton interpolation polynomial using the divided difference coefficients, evaluate the polynomial to estimate the required energy generation value. So for the interpolation model formulation, coding implementation and verification, both interpolation methods were implemented using appropriate coding technique to reduce manual calculation errors and improve accuracy. The codes were developed to generate interpolation polynomials and compute estimate values automatically. The estimate results obtained from Lagrange interpolation and Newton divided difference were the compared to verify consistent and accuracy. Thank you.
I'm Elizabeth Gray, matrix number CE240001. I'm going to explain the Lagrange interpolation manual solution. For the first numerical method, we use the Lagrange interpolation method to estimate the solar PV generation at year 2018.5. The given data consists of solar PV generation from 2016 to 2020, and our target values lies between 2018 and 2019, so interpolation is suitable. Linear approximation, our first order. We apply the linear interpolation data using from 2018 to 2019. A linear Lagrange polynomial is constructed using two data points. After substituting the values into the formula and evaluating at x equals to 28.5, we obtain solar PV generation answer 468.9895 gigawatt per hour. This value is only a rough estimate because it assumes the data varies linearly. Quadratic approximation second order, we improve the accuracy using quadratic interpolation, which involves three data points, 2017, 2018, and 2019. A second order Lagrange polynomial is formed using these 3 points. After substituting data and evaluating at 2018.5, the estimate values becomes 478.86 gigawatt hour. The result is closer to expected value, showing that increasing the polynomial order improves accuracy. And next, cubic approximation, third order. We apply cubic interpolation using 4 data points from 2017 to 2020. A third order polynomial is constructed, and the function is evaluated at 2018.5. The estimated solar PV generation is 475.845 gigawatt hour. This value is very close to the final answer, indicating good convergence. And lastly, our quadratic approximation for order. We apply quadratic interpolation using all of 5 data that we have from 2016 to 2020. A four-order Lagrange polynomial is constructed, and when evaluated at 2018.5, The result obtained is 475.92 gigawatt hour. And this is the most accurate result since it uses all available data. For the second numerical method, we apply Newton's divided difference method using the same solar PV data from 2016 to 2020. This method is particularly suitable for tabulated data and allows the interpolation polynomial to be constructed progressively. Step 1, zero divided difference. First, the zero divided difference are simply the original solar PV values for each year. Step 2, first divided difference. Next, the first divided difference are calculated using the formula, which is the difference between consecutive function values divided by the difference in their value x values. These values represent the approximate rate of change between consecutive years. Step 3, higher order divided difference than the second, third, and fourth divided difference are calculated using the previously obtained values. Each higher order divided difference captures more curvature in the data. From the calculation, we obtain the final fourth order divided difference coefficient. Step 4, construct Newton's polynomial using the divided difference coefficient. We construct the Newton interpolating polynomial. The polynomial is expressed in terms of x minus x0, x minus x1, and so on, making it efficient for computation. Step 5, evaluate the x 2018.5. Finally, we substitute x 2018.5 in the Newton polynomial. After performing the calculation, the estimated solar PV generation is 475.92 gigawatt per hour. Now I'll explain the MATLAB coding implementation used to verify our manual calculation for estimating solar PV electricity generation at year 2018.5. Okay, for this MATLAB solution, we compare two numerical interpolation methods. Okay, first we'll be using the Lagrange interpolation. First, we need to define the data in MATLAB, which x represents year 2018 to 2020, and variable y represents the corresponding solar PV generation in gigawatt hours. So our target year, we don't want to estimate, is define x target equals to 2018.5. The data is exactly the same as data used in the manual calculation. So next, we implement the Lagrange interpolation method in MATLAB. The variable n is used to store the number of data points, which is 5 in this case. The variable y is initialized to 0, and it will be stored in the final interpolated results. A nested loop is used to construct the Lagrange polynomial. The outer loop represents each data point, which the inner loop calculates the Lagrange basis polynomial by multiplying the product terms involving the target year and the remaining data points. So each basis polynomial is multiplied by its corresponding solar PV value and added to the total sum. Since 5 data are used, so the resulting polynomial is a fourth order Lagrange interpolation polynomial, which is consistent with our manual solution. After the loop finishes, MATLAB displays the estimated solar PV generation at 2018.5. The result obtained using Lagrange interpolation is 475.917 gigawatt hours. This value matches our handwritten calculation, confirming the correctness of the method. Solar PV data from 2016 to 2020 is first defined in MATLAB, where the variable x represents the year and y represents the solar PV generation in gigawatt hours. Next, the total number of data points is stored in the variable n. A square metric dd is created to the store to divided difference table, and the first column of the table is filled with the original solar PV data, representing the zero divided difference. The divided difference is the then constructed using nested loops. The outer loop controls the order of divided difference, while the inner loop calculates each divided difference using the difference between two previous values divided by the difference in their corresponding x values. Once the divided difference is completed, the Newton interpolation polynomial is then evaluated. The variable newtons is initialized with the first divided difference coefficient, and a variable called product term is used to store the product of the terms involving the target year. Then a loop is then used to evaluate the polynomial at x equals to 2018.5 in each iteration. The product term is updated and multiplied by the corresponding divided difference coefficient, and then the result is added to the total sum. So finally, the estimated solar PV generation at year 2018.5, when we run, it will be displayed at the command window. So the result obtained confirms the accuracy of the Newton's divided difference method. Now for a comparison between two codings, the same solar PV generation data is then used for 2016 to 2020 to ensure fair and accurate comparison. So the two numerical methods are implemented in this MATLAB coding, which are Lagrange interpolation method and Newton's divided difference method. Both methods are used for the same target year, 2018.5, then are coded with single script so that results can be compared directly. The Lagrange interpolation coding uses nested loops, as we mentioned before. Then the Newton's divided difference coding constructs a divided difference table. It evaluates the Newton's interpolation polynomial as the same target year. And addition for this MATLAB coding is revealed in polyfit function, so it uses the vertification method with shift x values applied to improve numerical stability. When you run the coding, the output will be Lagrange interpolation, Newton's divided difference, and MATLAB polyfit all produce the same estimated solar PV generation of 475.9170 gigawatt hours. The value is then consistent with our manual calculation, confirming that both numerical methods and the MATLAB coding are correct and reliable.
Assalamualaikum, a very good day to everyone. My name is Mohammad and I will take a part presentation for this discussion. Okay, The renewable energy data for the year 2018 was analyzed using Lagrange interpolation and Newton's divided difference methods. Both methods produce similar estimated values, showing that they are reliable for interpolating data within the given range. Lagrange interpolation is simpler to apply but becomes less efficient with more data points, while Newton divided difference is more flexible and efficient for adding new data. Overall, both numerical methods are effective tools for analyzing engineering data. In conclusion, Lagrange interpolation and Newton's divided difference were successfully applied to analyze the renewable energy data for the year 2018. Both methods provide accurate and consistent results, demonstrating the effectiveness in numerical data analysis. While Lagrange interpolation is simple and straightforward, Newton divided difference offers great flexibility for larger data sets. These numerical methods are useful tools for solving real engineering problems involving data estimation.